right. Want to do a problem where I guess I haven't seen a lot of you for a while. Sorry, I was really sick over the last week, but time to get back into it. And the problem at hand is to find the equation of a tangent plane. And I think it's good to know the idea. I don't want to do the derivation. Um, the book does the derivation, but it leaves out one critical point. And the idea is the following in terms of finding a tangent plane is you have some sort of a surface, and I've said now a million times it's hard to draw a surface. But if you imagine on that surface, so I won't even draw the surface, but there's the x-axis, say, the y-axis, dog barking, and the z-axis. You can imagine that my dog is interested in something. You can imagine that the surface is here, that if we just look along the x direction and we use our partial derivative, we would get we don't get a tangent vector. This is important. We don't get a tangent vector from the partial derivative, but we get the slope of a tangent line. Slope of a tangent line. If we think of this as the tangent line, and I project this onto the xz plane, imagine you take this and you project it on the xz plane, you would get this line in the xz plane. Now we want to get a vector from that. And how can we get a vector from that? Well, since it's now we've projected it, it's in the xz plane, that y is always 0. And if y is always 0, we just need some vector here in the xz plane. We could take the magnitude or the value of the x coordinate of that vector to be 1 arbitrarily. If I take the value of x to be 1, then the value of z will be given by the slope of that line, which is the partial derivative. Now, if you look at the book, and again, we're in 4.4. 4.4, what did I just say? I just said make y equal to 0. Arbitrarily make x equal to 1. And then z will be the partial derivative with respect to x. You'll see that that's what they've done. And they're in their derivation for the tangent plane. If you look, this is right after definition. If you look right after definition 4.24. If you look right after it, they derive they derive this formula right after they present this formula. And you'll see in the matrix where we determine the determinant, which gives us the normal vector for the tangent plane, that they have these rows. Well, this is one of them right here. They have one row that looks like 1, 0, this, and then they have another row which looks like 0, 1, and then the partial in the y direction. And that's where they've gotten those from. So you use the partial to give you a tangent line. Now that tangent line will be contained in the tangent plane. We project that on the xz axis. The partial gives us the slope of this line. Then we construct, and we could have constructed any number of vectors, but we construct maybe what would be the simplest or most obvious vector, and that's where we take the x coordinate to be 1, and we let the slope of this line give us the z coordinate. So this right here that I'm pointing to, this row, this is a vector in the xz plane, which will be in the tangent plane. This is a vector in the yz plane, which will be in the tangent plane. How do we find the equation of that plane? We take the cross product of these two vectors. That gives us a normal vector normal to the tangent plane. We have a point in the plane because we're given a point on the plane, which is the point on the curve. And then you put that together and you get this right here, this equation, which is the equation of a tangent plane. Now, after all that, there's really, really good news. Let me just grab something to wipe the board off with. And the really good news is you don't have to rethink that. And you certainly don't have to rederive that. What we have now is a flat out formula, if you will. And the formula is at 4.24. Let me just write it up here just so I can take a look at it too. And I want to do an example where we actually find an equation of a tangent plane. So it says z is equal to f of x sub naught, y sub naught. Now, x sub naught, y sub naught is the given point on the surface. So it is as if someone said, hey, I want you to find, it's not as if, someone has given you a particular point at which you will find the equation of a tangent plane. Now, it's not at this point. This is the z coordinate. The z coordinate of the point on the surface. The z coordinate given by the point x sub naught, y sub naught. Then plus the partial derivative with respect to x at that point. I'll draw some new drawings there. Times x minus x sub naught. I mean, this is a fairly, I guess, burly formula here. I guess I should continue in blue here. Plus the partial at that point. Now, no matter how intense or epic that formula is, if you look at it, it has all these pieces. And we just have to determine the pieces, and we're done. Now, what pieces are we going to have to determine? Well, we're going to be given a function. So the function's given. We're going to be given x sub naught, y sub naught. This is a calculation. So this is a straight up calculation. We find a partial. We have rules for that. So that's not an issue. I mean, I'll do an example, but we have rules for that. So finding this is not an issue. This, we just plug in this point right here. We use our derivative rules to find this, and we plug in that point there. So strangely enough, finding the equation of a tangent plane really is not that difficult because it's either a calculation, a plug-in, or we use our rules. We have existent rules. So you've certainly noticed by now that the book tends to give a worked out example and then an example for you to do on your own. So let me scroll down here and I'll do the one that they have not worked out. So let me do, which one looks like a good one to do? Well, they've got, and this is pretty classic, right? I see an example which involves polynomials and one which involves trigonometry. Maybe I'll do them both. I don't know here. Let's just do this here. Let me write this one down here. This is a checkpoint 4.19. So 4.19. So let me do that example. And the equation looks like f of xy is equal to x cubed minus x squared y plus y squared minus 2x plus 3y minus 2. So that's the function, and they gave us the point, so at, and this will be the x sub naught, y sub naught at the point negative 1, 3. Well, like I said, after all this, you think this is going to be the super difficult thing, but it's sort of oddly easy to do. We just have to construct the pieces and then put them all together using that formula. Okay, so I don't know what I want to do first. Maybe we'll just find f of negative 1, 3. This is this piece right here. So we just have to plug everything in here. And that's just a matter, like I said, of doing a calculation. So how you want to go about doing that, that's your own business. I mean, I don't care how much work you show at this stage of the game. We put a negative 1 in there, we would get negative 1 cubed. If I put a negative 1 in there, I get 1 times 3, which is 3, so minus 3, and then plus 3, and then what, minus 6, and I almost made a silly mistake there, but negative 2x, so plus 2, and then plus 9, minus 2. So let's see, negative 4 plus 3 is negative 1, minus 6 is negative 7, plus 2 is negative 5, plus 9 is 4, minus 2 is 2. So all that is 2. So I don't think I need to leave that there for any reason. So that's 2. Now, one thing to keep in mind, I'm not making a graph, but there is a surface here. And where are we on that surface? We are at the point negative 1, 3, 2. So the actual point on the surface is negative 1, 3, 2. Now, if I was making a graph, that might be important to bring that to the forefront and graph that particular point on that surface. What do we have to do next? Well, I need to find a couple of partial derivatives. So let's find the partial derivative of f with respect to x at that particular point. But let's just find the derivative first. Well, you have to. So let's see. With respect to x, so this is 3x squared. With respect to x, y is a constant. So the derivative of this chunk right here is just negative 2x. Y. It might have been more consistent if I had said, in fact, let me go ahead and do that. So negative 2yx. Why? Because I'm looking at y as a constant. And normally we would write the constant out in front. You don't have to, but that would be more normal. The derivative of y with respect to x is 0. It's a constant. The derivative here is negative 2. The derivative of that is 0, and that is 0. So there we go. So not too bad. Now, what am I going to have to do? Eventually, I'm going to have to put that given point in there. So maybe let's go ahead and do that now. I could have waited, but negative 1, 3. Let's see if I put a negative 1 in here. What do we get? 3. I put a negative 1 in there, squared, positive 1. Put a negative 1 in there, so positive 3 in there, so plus 6. Minus 2, 9, minus 2, 7. Hopefully double checking on my calculations. It seems like such a shame to do all the complicated stuff and then get a problem wrong because I just didn't add numbers correctly. I didn't do the arithmetic right. Okay, we're going to need those 2 bits of information. Let's find the derivative with respect to y of this function. So with respect to y, that's a constant. The derivative of a constant is 0. The derivative here is minus x squared. The derivative here is 1. The derivative of this is 0 because we're taking the derivative with respect to y. Here's plus 3. And then there, that's 0. So we can add those 2 together, plus 4. And now let's find the value of the partial derivative evaluated at the given point, negative 1, 3. So put a negative 1 in there. So what do we get? Negative 1 plus 4. So we get 3. Okay, and now we just have to put the pieces together, and we're done. And there'll be one implied issue at the very end of this. Nonetheless, let me go ahead and do it. Using this formula up here, we have z. Let's see if I can find a better marker somewhere. Z is equal to, this we've already calculated. That wound up being 2. So 2 plus, where's the partial derivative of f of x evaluated at 0.7 times x. Now it's minus x of naught. X of naught is, well, let me write it in like that for a minute. So minus 1, right? That'll wind up being plus 1, but just so that we can see where we substitute things in. And then plus the partial derivative of the function with respect to y evaluated at that point. We did that. That was, where did I do that? Down here, 3. And then times y minus y sub naught, which was 3. And, we should simplify this if possible. I suppose 2 plus 7 times x plus 1 plus 3 times y minus 3. There's the answer. So oddly easy to do. Which probably the most difficult thing is visualizing this. So again, the question did not ask us to visualize it. The question did not ask us actually to do anything with this, not even make a graph. This is a good place where you could, use a grapher to make a graph. Another approach in terms of making a graph is to think about what does this mean? If you remember how this relates to a normal vector, this sort of equation. If I was going to make a graph and utilize the normal vector, I would rewrite this. I would get the z over on this side, and I would think of it as this. I would think of it as 7 times x plus 1 plus 3 times y minus 3. Remember, I'm going to get everything over on this side, and then I'll switch sides, but get everything over on this side. And what would we have here? Well, I probably would want to write it like this: minus 1 times z minus 2. So I did a little bit algebraic footwork there, equals 0. This was that standard way of writing the equation of a plane where 7, 3, negative 1 is the normal vector. Now, if I graph the normal vector, that will allow me to imagine the plane itself because it's normal to that vector, right? So whatever that vector looked like, even if I made a super quick graph here, 7, 1, 2, 3, 4, 5, 6, 7, 3, go out 1, 2, 3, 1, 2, 3, and then down 1. So the vector would look like this. The plane is perpendicular to this. So the plane perpendicular to this might look something like this, where there's a right angle like that. However, this plane is situated or contains the point negative 1, 3, 2. It contains the point negative 1, 3, 2. So negative 1, out 3, and up 2. So I would think of taking this plane here, which I have going through the origin, and pushing it back on this point here. So this plane maintains the same orientation in three-dimensional space, which is to say it remains perpendicular to this vector right here. This question did not ask us to do that. We didn't have to do it. But that, to me, seems like an obvious thing. And then, of course, the big elephant in the room is I didn't even graph the surface. In this, move back here, is supposed to be a tangent plane. A tangent plane to what? To the surface, which I never graphed, which would be the most difficult thing of all to do, but the question didn't ask us to do it. And I think you could, without too much difficulty, at least you could throw this into Desmos or some other grapher, and you could get an image of what the surface looks like. And so you might want to do that just for fun. It didn't ask me to do it, so I'm not going to do it here. So hey, I'll end that video here. I think that's good for tangent planes. As long as you have this formula, you're good to go on tangent planes. All right, and my computer just cut off. All right, more videos to come.